Composite construction is nothing new in this industry. I don't need to tell about the benefits of that. In the past few years, when we have gone through a lot of projects, starting from the planning part of we have been really involved mainly in the design and the construction supervision part of it. So that's when we understood the requirement of a pre-planning stage of a composite construction to the final implementation of a composite construction. Composite construction has been well used in the last 2 to 3 years in all over India. The progress is a little slow in different parts, but then yes, it is progressing, and I don't need to talk about the benefits of that at this stage. So there is a workflow we would like to present for the composite construction, which I would idealize if you want a very effective or economic composite construction. It starts with the architects, and I'm talking about the amazing architects and amazing architecture we have over here. And the client and the architects, they need to really confirm that yes, they want to go in for a steel or a steel composite construction. Now, once that is confirmed, the designer and the architects need to sit and visualize why and when they want the steel composite construction. And then once that is done, they need to understand the limitations, or they need to understand the the dreams of the architect to implement that on site. So once the designer or the structural engineer and the architects are through with their pros and cons, and they finalize, finally they come up with the final architecture, which actually will be giving you an economic and a very effective composite construction design. Then comes the structural detailing part, and then followed by the pre-construction planning. I've given a workflow chart. It's not complete yet because I've given a segmental-wise workflow chart. So even in the pre-construction planning, I believe there's a role of the architect, the role of the consultant, and the role of the contractor. It's very important because if you don't pre-plan your construction, you are going to lose your money, you are going to lose your time, and both are very valuable. And we are going to lose our resources as well. A few days back, one of my close clients, he was quite open to a structural steel building. So I was sitting with the architect, and then we were framing out a typical structural building, a residential building, not a commercial building, a residential building where I would be using steel, and we would be following composite construction, and then we would want to economize on the steel structure usage. Okay. Okay. If you just notice, I've just circled the column locations in purple, and I've given a grid spacing of 8 by 8. I'll explain later what is the economic grid spacing we have come up to, and it's not only with us, it's all over the world. They follow this sort of grid spacing in any of the residential or commercial buildings. So this left portion is what the architectural plan looks like for a typical construction building. And I've placed the column layouts over here so that you can just have a look at how the spacings are going. This is an 8-meter span, and this, of course, goes out to 8.5, 9 meters, 8 again, and then 8.5, 9. And on the right side, I sat with the architect and I showed him that how I would actually frame a beam or make a beam layout based on his architecture. If that's acceptable to the architect, we'd go ahead with that. So what we do is that we frame in a column. We call these the main girders, the yellow beams. That's the girder beams. They frame into the columns. They are the main load transfer members. And what we call in blue are the beams. So we differentiate between a girder and a beam. It may be joist, it may be I-section, it may be anything. But I'm just, for a terminology, I'm just differentiating that. The girder is the load transferring member. So the beam will effectively transfer the load to these girders, and then the girders to the columns. But if you see something, we generally frame in the load transfer girders to the flange of the column. We don't use the weaker axis of the column. Because I don't want, that's another, once I frame into the weaker axis, I'm wasting my resource and my money on the connections. I don't want to do that. So once we do that, then comes we use a metal deck, the embossed profile sheet, which is known to the market, and then what we use is the composite shear studs. This is how a typical spanning of a shear stud would look like. Planning of a composite deck would look like. Now, in this building, you'll see the number of columns have been reduced a lot. We don't use intense columns because we want to economize on that. Number two, we don't keep a spacing of more than 2.6 meters beam to beam. That's for using a 1 millimeter thick metal deck. You have the variation of using 1.2, you can go up to 1.6. And once you go into 1.2, 1.6, you can increase your spans. If the architect says, no, I don't want an intermediate beam over here, then you say that fine, we go in for the next decking system, 1.2. So realize something, that we are actually fixing what deck to be used, what metal deck to be used, what beam system to be used, while in the architectural stage. We are not designing after we get the architectural drawing, no. We sit with the architects, we plan it out, so the architects know where my limitations are, and I know where the architect's limitation is. Once we do that, we come up with the final framing. See, in general, a composite construction or a steel building, we don't go beyond, we never want to go beyond 5 kg per square feet. That's actually true. I mean, even with 250 grade of steel. If you go for 350 grade of steel, then we can go up to around 3.85 to 4.25 kg per square feet, which is quite economic. So the economical grid system for a commercial building would be something like this. It'll be either a 6 by 8 grid, or a 8 by 8 grid, or a 8 by 10, or a 8 by 12 grid. And if you see again, we use the beam system generally frames into the shorter beam. It doesn't frame into the longer beam. Why? Because we don't want to compromise with the depth of the beam, which is transferring the load. So these transfer beams then transfers to the main girders. We use the transfer to the shorter girder, which then connects to the column flange. So this beam, actually, it's a longer span, but it doesn't take so much of load so that we restrict on the depth of the beam. Similarly, if we can use the same grid system for 8 by 12 and 8 by 8 grid systems also. Now for residential buildings, we don't go beyond 6 by 8 or 8 by 8, because if you're going beyond that, you're increasing the building height. Because once your beam depth increases, your building height also increases. We don't want that. Because once your building height increases, you're again hampering the economy of the building. So a 6 by 8 and an 8 by 8 would be an economic span grid for any residential buildings. Okay, now during the pre-construction or the pre-planning stage with the architect, I also mentioned few things. The deck system we are using, anyone's deck system we are using, we generally ask the width of the deck. The width of the deck is very important. I'll tell you why. Because once you place the decks one after another, you don't want the crest of a metal deck to fall just on top of the flange of a beam. Because if you do, you will not be able to put any shear connectors on them. Your beam flange is unused. You're not using any of the forces of the beam flange. So once you plan your deck width, you have to make sure that the trough of the deck falls on the beam flange so that you can weld your shear connectors, and your load transfer system is with both the beams, not restricted to one beam. Another system of design which we follow, and I also sit with the architects on this, is that we define or we differentiate the structures into two parts. One is a lateral system and one is a gravity system. We don't want all the beams in the structure to take in lateral or seismic or wind load. No, we don't want that. It's going to penalize the beam depth. So what we do essentially is we put a framing. In the structure, there'll be certain columns which will be designed for the lateral loads, and those columns are going to be connected by lateral beams. They are going to be taking in the lateral loads and the seismic or the wind loads along with the dead and live. And there will be another set of beams which are going to be designed as gravity beams or gravity columns. They are only and only going to be designed for dead and live, and the columns are going to be designed for dead and live. You know what will happen? You will economize on the beam depth and the beam column depth, column sizes. That's for sure. Because once you define this system that yes, I want this, see this red mark, the red columns and the red beams are the lateral grids. They take in the lateral forces. And the ones in gray, they are taking in only the dead loads and live loads. So you are not actually increasing all the beam depths. And where I would place the lateral frames, where I would have a wall below, or a solid wall where I don't have any openings, or where I can place a bracing system. Because if I can do that, then the architect can tell me, yes, you can go ahead with this row of columns, or you can go ahead with this row of beams and put it under lateral loading, because I can avoid the openings over there. Let's say for a staircase, 2 walls of a staircase, they don't have any openings. I can use that for a lateral framing. I can put some cross bracings, or I can put some moment connection frames. Once I do that, I can avoid a lot of those beams. So this is a typical actually residential building we had done for another project in Calcutta. And we, by the way, we used hollow sections for columns. This was just, it was a hollow section column design. No I section, no built-up sections. So over here, you'll see the grade, most of the beams are gray members. It's a 4-storied building, G+4. And what we did was, we did some lateral framing, one over here, one this side, and one over here. So once we distributed the lateral frames, the other beams were designed under gravity loading. Economic design, hardly any depth. So over the years, this study of this chart is taken from the internet, of course, and we've quite identified with the chart and the beam depths we get from that. For a composite beam spanning between 6 to 15, the depth of the beam would range between 400 to 800. So up to 8 meters, or let's say up to 8.5 meters, I wouldn't go beyond 400. No, I don't want to go that. Maybe from 8.5 to 12, I would range it between 5 to 550. But beyond 12 meters to 15 meters, I would go up to 700 or 750, yes. And if necessary, if the loading is really on the higher side, 750 or 800 would be necessary. Otherwise, no. Castellated beams. Castellated beams, of course, I'm talking about the cellular beams. They are available in India, but they are not very easily used. Generally, they are used in commercial where you have ductings and the hollow pipes which go in through that. And then we have the fabricated roll sections. I'll give you an idea of what we use. We have developed some typical section of beams which are generally not used anywhere. So these we call them the fabricated roll sections. See, the rolled beams are the typical composite beams which everyone uses. It's very common in India. This project is in Texas. It was a bank project we were doing. This is a structural system we developed. There's no other structures over here which has been using this form. Hollow sections people have been using for architecture. Hollow section people have been using for beauty, even for the roof system. But we use hollow section beams for composite beams for structural building. And we have successfully done that. We form a verandal girder. What happens? Look at the benefits of this. The openings allow circular and rectangular ducts, any size. We can vary the opening size based on the architectural requirement, based on the ducting requirement. We can do that. We have done that for this project. And you'll see all of them are hollow sections. And we use these hollow sections to form the beam and then have a composite deck slab on top. People are yet to use that. It's a very, very strong form. Because of the biaxial strength of a hollow section, it's really underutilized section, underutilized members of in India. People need to realize the benefits of hollow section. It can actually transfer any structural load of any building. And it has the benefits, of course, giving the height, depth also can be restricted. For a 14-meter span, we have not gone beyond 500 meters, 500 millimeter depth. That's for one of the projects which we did in Calcutta and Globe Cinema. Another use is that fabricated castellated. We've also used this for residential building. So what we do is that, I don't know whether you're able to see this. This is a fabricated plate, and we define how to cut it, and then make it into a castellated beam. We fabricate that. And it's done on site or in a workshop. We can do that. Now, during construction, I've seen people just punching in with the shear studs with the Nelson stud gun. No, it's not supposed to be exactly like that. People have to specify where to punch in. The depth, the distance from the stiffener, the central zone, that is this part, is called the stiffener for the bending, for the metal deck. The metal deck is basically what? It ensures a one-way spanning system for the slab, and what it does is, it acts as a bending reinforcement for that. So when you're using a metal deck, all you need is a minimum reinforcement on the top of the concrete, that's it. And the thickness of the concrete above the crest, the maximum you need to, the minimum size you can use is 100. Because 75 would be good, but as for the fire protection laws, you need to have a 4-inch topping on that. So with a 100 slab and effectively 100 slab over the crest, you can actually go in for residential or commercial buildings. We have gone in for the commercial buildings. So the placement of the shear stud beside the stiffeners is very important. It may be a double shear stud or it may be a staggered shear stud. We need to follow the distance, and this distance is specified. It is very essential to follow that. Once you do that, your slab is bound to act in unison with the beam with full 100% efficiency. So after the design part of that, how we, or what are the things we give to the site beyond the construction or detailed drawings while doing a composite building. So this is a typical layout of a building which we did, steel building, a commercial building, and we gave it to the deck supplier. What he essentially did, because he saw the shear stud, these are the number of shear studs per beam. That's how we designed it. Once he did that, what he essentially gave me is this drawing. So he formed the layout of the deck. So you see, each of this is like it has the deck number, it's MP103. It has the deck length. For this one, it's 5250. For this one, it's 5000. This one is 4500. So these are the decks he specifies in the layout. It's not only on the drawing. He will send the material based on this bill of material. The MP101 has a length of 6480. It is 19 in quantity of galvanized sheet. And once he does that, you are assured with the contractor that yes, I need to place this number of deck in this place. Okay, so when you get the deck, you have to stack it according to your constructional sequence. You can't just stack it as per your requirement. If you do it as per the constructional sequence, you are stopping the waste of time for any of your construction. So in the pre-construction planning stage, we actually also, along with the contractor, and we are involved the architect also, we do some workshop fabrication planning. Which girder, which framing is to be erected first, which material is to be supplied first. We ask the contractor for his limitations, how much he can transport. We base the design of the connection based on his limitations or his transportation length. And based on that, we give him the drawings. We develop the drawings based on discussion with him, and not only based on where we can find the connection. We stop the wastage of that. Then we have a segmental transportation planning. That is a phase-wise transportation planning, because at site, it's not always possible to store all the material which comes. So we plan with the contractor where and how much material in which phase of time he is going to store, and where he will be, which frames he will be erecting. So then once the material is done, we then call it the indent markup stacking. In the indent markup stacking, we actually tell the contractor which are the materials where to store, where to stack. And we as a designer or as a consultant, we get involved in this totally. In the supervision, in the planning of the stacking, in the planning of usage, and the planning of redistributing the material during fabrication and erection. Essentially, in a building, I would prefer to erect the lateral frames first, followed by the gravity frames. I just explained a difference between lateral frames. So because once the lateral frames are up, you know that your structural systems, if they can both go parallelly, but you can't have the gravity structure up before the lateral. So once your lateral and gravity is up, even during construction phase, you know that even under adverse weather conditions, your structure is going to remain safe. It will not yield to any of the forces. So this is the next work flow chart. Once we start erecting the frames, erecting the members. It starts with erecting the steel with lateral gravity, positioning the floor decking, and then we make sure where and how to trim the decks based on the columns or beam ends and how to do that. We have to sit with the fabricators or the deck suppliers where to trim. During construction of a composite building, during green concrete stage, there is no composite action. And you have to understand that I know we are using a metal deck, but a metal deck and a beam can be subjected to a deflection due to a pre-composite dead load or a pre-composite live load. So do we put a prop? Yes, we can put a temporary prop. But what the prop does is, it avoids any cambering of the beam which is required. So while erecting the frame, after erecting, we don't erect one floor at a time. See, that's the beauty of composite construction or steel building. You can erect the entire frame, and then parallelly, you can start putting in the decks. And essentially, a good planning of the beam and the deck system would essentially mean that their deck actually ends, your deck lengths and everything are matching with half the width of the beam flange. And then your deck's trough, that is the lower portion of the deck, is on the flange of the beam. Once the layout is done, then comes the cutting part. This is what I was just telling you. Once we have this deck system, we have to make sure that the cutting and the trimming of the decks are done very, very effectively. We don't want any, because you can't weld back the deck. So this is very important during construction, and it has to make sure that whoever's doing that, there has to be a proper supervision during that. So cambering is something we generally, we have used in a lot of our Western world projects. In US, cambering is a very common thing. It's not in India. The pre-camber comes in because due to dead load or during the green concrete, the beam deflects. So that's what I was mentioning. If you want to prevent a cambering system in India, you have to put a temporary prop during construction. That's a temporary prop. You can use that. These are generally why we can avoid cambering and how what is the effects of cambering, I mean, while doing it. So pouring a slab of varying thickness over the beam, that's how you can avoid cambering. Or you can use the oversized beam, which we don't want to use. The effective and the most cost-effective or the economic way is to use a shoring. That's a temporary prop with having the concrete of the lower floor reached at 70%, 75% strength. For the decking, before the shear stud is put in the deck or welded into the deck, we have to make sure the deck is in place. And for that, we use a tapping screw. And that tapping screw is not to be screwed in with any, just a screwdriver or any local made material. It has to be done with a tapping gun because it has to penetrate the flange of the beam effectively without disturbing the deck. After that, we have the ceramic rings which contain the fumes of the stud welding gun within the shear stud. Once that is done, once the shear stud is welded, we knock off the ceramic with a hammer, and within a span of 20 to 25 seconds, each stud has to be tested with a knocking hammer. If the hammer test is succeeded, then you can go ahead with the stud, or else you have to remove the stud, replace it with another new stud. You can't reuse an old stud. This is how typically how a stud gun works. That you place the stud, and once you press it, actually the stud comes up, the welding is done. Then once the base material is molten, and you press the stud back, and then when your stud gets welded. After this is the last stage where you place the concrete, prepare the slab, and remove the props. This is how a typical thing would look like. You have the metal decks with the studs, and minimum reinforcements, absolutely minimum reinforcements. There's a cantilever span, and then once it's done, it looks absolutely like a regular building. So this is just an image of this is during construction, and that's actually how a composite building would actually look like after thing. So this is another one. This is in fact in Kolkata, we've done one of the projects over here. So this is during the construction phase, and this is actually the finished of a composite building. So I don't think you will have it. This, I'd just like to end my thing. This is one of the buildings which we did in Texas. In Texas, we've done a huge amount of composite buildings. This building, actually, you won't understand this is made of composite, but it is. These are hollow columns, again, columns being used with hollow sections and with I-beam framing into the columns. A typical composite building. In the Western world, one thing which we don't do over here in a composite building, the roof system, if there is no further expansion to be added, the roof system is defined as a non-composite. They use metal deck, but they don't use the embossed profile sheet. They use the regular profile sheets, and that's why you save again. You can actually, so over there, on an ideal composite building, I will not go beyond now with, we are using one of those 350 grade of steel in one of the Tata Metalics project in Kharagpur with one of our clients, Ande. So over there, we are using 350 grades of steel. And with 350 grade of steel, actually, you can have a lot of control over the beam depth and over a lot of these the section usage and economy. So you can go with 350, I would not go beyond 4.25 kg per square feet. That's an effective design of a composite structure. Thank you.